how to draw this function. Alright. So in order to draw this function, first of all we have to find what are the vertical asymptotes this particular function has. Right. So first of all you have to find vertical asymptotes. So what are the vertical asymptotes? So in order to find the vertical asymptotes, you have to see what is the numerator, what is the denominator of this function. Right? If it's a rational function, the denominator cannot be equal to 0. Here, x plus 1 whole thing square cannot be equal to 0. It cannot be equal to 0. Okay. So if x plus 1 whole thing square is not equal to 0, which means x plus 1 cannot be equal to 0. So x cannot be equal to minus 1. So then we can say hence x is equal to minus 1 is a vertical asymptote. Alright? Okay, this is the first step. And now the second part is we have to differentiate it and we have to find the turning points. Right? So find the turning points. Right. In order to find turning points, you have to find the first derivative of this function. So if dash x, that's going to be equal to x plus 1 whole thing square. So this is the format u over v format, right? This function is a u over v format. So you know how to differentiate a u over v format. So first of all, you have to start from the denominator. Right? Denominator into differentiation of the numerator, that is 1, minus the numerator into the differentiation of the denominator. Right? If you differentiate this denominator, it's going to be 2 times x plus 1. Right? Divided by the square of the denominator. The square of the denominator, x plus 1 to the power 4. So you have to simplify this. If dash x is equal to this is x plus 1 whole thing square, there's x plus 1 here, so you can take x plus 1 as a common factor. So it's going to be x plus 1 minus 2x divided by x plus 1 over to the power 4. So if we simplify this, it's going to be if dash x is equal to x plus 1. If you simplify this one, x plus 1 minus 2x, it will be 1 minus x divided by x plus 1 to the power 4. Now, if dash x is equal to 1 minus x divided by, you can cancel these two, right? So, it's going to be x plus 1 to the power 3. So, this is the first derivative of the given function fx. Alright? Alright guys, now we have to find the turning points. In order to find the turning points, we have already found the first derivative of this particular function. You have to equate this first derivative to 0. We know that f dash x is equal to 1 minus x divided by x plus 1, right, to the power 3 is equal to 0. So the solution of this one. So if 1 minus x over x plus 1 whole thing cube is equal to 0, 1 minus x has to be equal to 0, which means x has to be equal to 1. When x is equal to 1, you have to find the corresponding y value, the y coordinate of this point, of the turning point. So when x is equal to 1, substitute 1 here, so you'll be getting the corresponding y value, 1 over 1 plus 1 whole thing square. So y is going to be equal to 1 over 4. So we can say that 1 comma 1/4 is a turning point. Yes, it's a turning point. So after finding the turning point, we have to show what kind of turning point is this. So here we have only one turning point. So you have to show that whether that turning point is a maximum point or a minimum point. So in order to do that, you have to draw a number line for x. In that number line, right, you have to denote the x coordinate of the turning point. That is 1. Apart from that, there is something else you have to denote in the number line of x. That is the vertical asymptote. Right? We know that vertical asymptote is -1, right? Okay, because here x cannot be equal to 0. X cannot be equal, sorry, not 0. x cannot be equal to minus 1. So you have to denote that minus 1 as well, right? So always remember there is a vertical asymptote here. There is a vertical asymptote here. Do not forget that, right? Minus 1. So here, these two values actually divide this number line into three parts, okay? So that is, right? There are actually three regions for x. The first one is x is smaller than minus 1. The second one is x is in between minus 1 and 1. The third one is x is greater than 1. Draw a diagram, draw a table, right? Okay. Here you have a vertical asymptote. Okay. Alright. This is f dash x. This is fx. Okay. F dash x. So what about f dash x in these regions? Okay. We have the f dash x, right? The first derivative of fx. So we had to find the signs, right, of f dash x in these regions. Right. Alright, guys, we have to find the sign of f dash x in these particular regions, right? So we have to find what is the sign of f dash x when x is smaller than minus 1, when x is in between minus 1 and 1, when x is greater than 1. First of all, we have to see when x is smaller than minus 1, what happens to f dash x? Okay, whether it's going to be positive or negative, right? Think of a number which is smaller than minus 1. Let's say minus 3, substitute minus 3 here. Substitute minus 3 here, right? It's equal to 1 minus minus 3 divided by minus 3 plus 1 whole thing cube. So f dash minus 3 is equal to 4 over minus 2 cube minus 8, right? That is minus half, smaller than 0. That is negative. That is negative. So in this region, f dash x is negative. Alright? Okay. So what happens when x is in between minus 1 and 1? Right? X is in between minus 1 and 1 in this region. Think of a number which is in this range. 0. 0 is a perfect candidate. Right? You can substitute 0. So f dash 0. That's the sign we have to check. Substitute minus 0 here. So 1 minus 0 divided by 0 plus 1 whole thing cube. So this is 1 here. 0 plus 1, 1 cube, that's going to be 1. So that is greater than 0. Greater than 0. Right? So it's positive here. So what happens when x is greater than 1? Think of a number which is greater than 1. Let's say 5. Right? When x is greater than 1, when x is greater than 1, right? Just imagine when x is equal to, let's say, 5. Right? So if dash 5, you have to see whether it's positive or negative. 1 minus 5 divided by 5 plus 1 cube. So it's negative here, minus 4. It's going to be positive, right? You don't have to solve it. You don't have to find an answer. It's better if it's only enough to find the sign. Okay. So this is definitely it's negative, right? So it's negative. So in this region, f dash x is negative, which means fx has to decrease with x, right? Here it's positive, which means fx has to increase with x, right? Always remember. Right? Here f dash x is negative, which means fx or y value has to decrease with x here. Alright? So definitely you can see here that is a turning point. That's a maximum point when x is equal to 1. Okay? Here x is equal to 1. Here x is equal to minus 1. But be careful, here you cannot take a turning point. Right? Sometimes after seeing this plus and positive, negative and positive signs near, right? Sometimes you may get confused that there is a minimum point here. Okay, there's no minimum points here, right? No turning points here because since this is a vertical asymptote, so there's only one turning point, that's a maximum point. So hence 1 comma 1 4, right, is a maximum point. Understood? Alright, guys. So the next thing we have to do is we have to find the horizontal asymptote, right? There are two types of asymptotes, right? Vertical asymptotes and horizontal asymptotes, right? In order to find the horizontal asymptotes, right? Okay, What you have to do here is you have to see what happens to y or fx when x tends to plus or minus infinity. Okay, right. So we have to see that we have to find the corresponding y values. So you have to find the limit, right, when x tends to plus or minus infinity, right, x over x plus 1 whole thing square. Right? Okay, it's a rational function. A rational function has two polynomials in the numerator and the denominator part. So for my convenience, what I'm going to do here is I'm going to expand this one. X squared plus 2x plus 1, right? Okay. In the numerator, you have a polynomial of first order. You have first order polynomial made of x, right? In the denominator, you have a second order polynomial made of x, right? So here we know that, okay, when you have a rational function, rational functions, and you are finding the limit of rational functions, right? Okay, and you're going to find the value of the rational function when x tends to plus or minus infinity, right? You cannot substitute infinity straight away. Okay, you have to do something else, right? Okay, so what you have to do here is you have to divide the numerator and the denominator. Okay, you have to divide it by the by x squared here, right? So how can I find that term which we are going to divide? Alright. So here the numerator, sorry, the denominator is a second order polynomial. So you have to divide the numerator and the denominator by x squared. So y is equal to limit when x tends to plus or minus infinity, you have to divide both up and down by x squared. So if you divide x by x squared, it's going to be 1 over x. Alright. Hope you could have understand this, right? If you divide this polynomial by x squared, you can separately divide each and every term. So it's going to be 1 plus. So if you divide 2x by x squared, it's going to be 1 2 over x plus 1 over x squared. So if you substitute positive or negative infinity here, this will be 0, this will be 0, this will be 0. So y is equal to 0 over 1 plus 0 plus 0. So here y is becoming 0. Okay. So when you are substituting plus or minus infinity to this particular function, right, the y value you are obtaining is a finite number, that's 0. So we can say that y is equal to 0 is a horizontal asymptote. Horizontal asymptote. So we have found the horizontal asymptote. You have to find an inflection point. Right? This is also very important. Okay, inflection point. So in order to verify the concavity of the graph, right, you have to find the inflection point. Right? So how can you find inflection point? In order to find inflection point, you have to find the second derivative of fx. Right? We already know what's the first derivative is, right? If you know the first derivative, you can find the second derivative of fx. So what you have to do here is you have to differentiate the first derivative again with respect to x. Right? So if you differentiate this one with respect to x again, right, it's a u over v differentiation. So you have to start from the denominator. So that is x plus 1 whole thing cube into differentiation of the numerator. That's going to be minus 1. Negative, right, 1 minus x. Right? The differentiation of the denominator, that is 3 times x plus 1 square into whatever inside x plus 1. Whatever inside the power x plus 1. So if you find differentiation of x plus 1, that's going to be equal to 1 divided by, right? So if you square the denominator, that's going to be x plus 1 to the power 6. Alright. Here you have x plus 1 cube. Here you have x plus 1 square. So you can take x plus 1 square as a common factor. So if you're going to do that, the remaining part here will be minus x plus 1. Okay. Here minus 3 times 1 minus x divided by x plus 1 to the power 6. So if you cancel it, right, if you divide these two, here you'll be getting x plus 1 to the power 4. So if you simplify this one further, right, it's going to be minus x minus 1 minus 3 plus 3x divided by x plus 1 to the power 4. So if you do it continuously, so f double dash x is equal to 3x minus x, that's going to be equal to 2x. Alright, minus 4 divided by x plus 1 to the power 4. So if dash x is equal to, you have to take 2 as a common factor. X minus 2 x plus 1 to the power 4. So this is the second derivative of the given function. Okay. So using this, we can find the inflection points. Right. Hope you understand up here. Right. Okay. The next step. Right. So for inflection point, the second derivative has to be equal to 0. Right. Okay. So equate the second derivative to 0. 2 times x minus 2 divided by x plus 1 to the power 4, and that is equal to 0. So 2 times x minus 2 is equal to 0. So x minus 2 is equal to 0. X is equal to 2. This is the solution. Right? So this is the x coordinate of the inflection point. Here you have only one inflection point. Okay. So when x is equal to 2, you have to find the corresponding value for y. So y is equal to, substitute 2 here. 2 over 2 plus 1 to the power 2. So it should give you 2 over 9. So 2 comma 2 over 9 is the turning, sorry, that's the inflection. So using this inflection point, you can find the concavity of the graph. So again, you have to draw a number line for x. In that number line, you have to denote the inflection point, which means the x coordinate of the inflection point and the vertical asymptote. Here also you have to denote the vertical asymptote, right? Okay, the vertical asymptote is common for both number lines, right? Previously we was drawing a number line for uh, we were drawing a number line for finding the turning points, right? Okay, so here also you have to draw another number line, right? Which one of the point is the x coordinate of the inflection point, and the other one is the vertical asymptote, right? Okay, here also you have to draw a table, right? Quite similar to the one we drew earlier, but it's big different. Okay, right. So here you have three different ranges, right? The first one is x is smaller than minus 1, x is in between minus 1 and 2, x is greater than 2. Okay. So here it's vertical asymptote. You have to be really clear about that. Fine. The first thing you have to do is f double dash x. You have to find the sign of f double dash x, right? So here it's fx. Okay. Alright. Always remember, right, when f double dash x is positive, the graph we can say that it's concaving down. Not concaving down, concave up, right? When the second derivative is smaller than 0, it is concave down. Okay, right? Concave up means if a graph has a part like this, okay, it's concaving up, right? This one is concaving down. It can be this graph or part of this graph. Okay, right? If the graph has a part of this or this kind of shape, right, we call it the graph is concaving up, right? If a graph has a shape like this, okay, right, we say it's concaving down. Okay, be clear about that. So we have to check the signs of the second derivative of fx in these regions, right? When x is smaller than minus 1, right? Here you have to check this one, not this one or this one, right? This one you have to check, don't confuse, okay? So think of a number which is smaller than minus 1. Let's say that minus 5, right? I'm substituting minus 5 here and I'm going to check the sign. Right? When x is equal to minus 5, if double dash minus 5 is equal to what? 2 times minus 5 minus 2 divided by minus 5 plus 1 to the power 4. This positive here, right? The numerator is negative. It's very clear, right? Okay. Because this one is anyway this one is going to be positive because minus 5 plus 1, that's minus 4 to the power 4, that's going to be positive. This is negative. So smaller than 0. So this region is negative. So when f double dash is negative, fx is, what about that? Concave down. Concave down. Alright. Okay. Hope you understood. When x is in between minus 1 and 2, right? What happens to f double dash x? So take a number with, which is within this range, within minus 1 and 2. 0, 0 is better. Right? Okay. So when x is equal to 0, check f double dash x. That is f double dash 0, right? Is equal to, substitute 0 here, 2 times, right? Minus 2. If you substitute 0 here, it's 1, right? It's negative again. Yeah, it can be. It's negative again. Right? It's concaving down. It's concaving down. So what happens when x is greater than 2? Think of a number which is greater than 2. 10. Substitute 10 here. 10 minus 2 positive. The denominator is going to be always positive, right? So you don't have to write anything in that. Okay, you can just do it in your mind. So it is positive. So this part is concaving up. Concave up. Okay. Alright, so in order to draw the graph, you need these tables, huh? This one and the table that you drew previous. Alright guys, now we have to draw the graph. So we have to include all the information that we gained so far. This is the x-axis and this is the y-axis and this is the origin. Here we have a turning point at 1, 1. And that turning point is the maximum point, we know that. 1, 4, 1. Okay. And at point 2, 209, right? This is an inflection point. This is 209 because it's obviously 209 is smaller than 1, 4. Okay, this is the turning point here. It's an inflection point. Okay, right? And this graph has a vertical asymptote, sorry, horizontal asymptote, that is y is equal to 0. So the x-axis is a vertical asymptote, right? And it has a, sorry, the x-axis is a horizontal asymptote, okay? And also it has a vertical asymptote at x is equal to minus 1. Okay, so when the graph reaches x is equal to minus 1, because here in this graph x cannot be equal to minus 1, right? That's why we have drawn a vertical asymptote here. But if, right, the x value reaches minus 1, the y value, the corresponding y value will reach infinity. It can reach positive infinity or negative infinity. We have to find that. Right? Always remember that x cannot be equal to minus 1, but x can reach minus 1. Right? It can take near values, it can take values near minus 1, right? Values smaller than, greater than minus 1 and values smaller than minus 1, okay? Right. So when x values reaches minus 1, we have to see, we can find, right, where does the graph actually goes to. Whether it's going to minus infinity or positive infinity. Alright, okay, now let's see that. Here, right, according to the first graph, the turning point graph, okay, when x is smaller than minus 1, right, fx actually increases with x, right? When x is smaller than minus 1, right, okay, the graph has to be like this, I'm sorry, okay, right, this is the graph. So when x is actually smaller than minus 1, x actually increases with x, right? So in this region, when x is smaller than minus 1, actually fx or the function y, the y value actually decreases. I'm sorry, it doesn't increase, it decreases. Okay. At the same time, right, what is the meaning of this vertical asymptote, sorry, the horizontal asymptote? When x tends to positive infinity or negative infinity, which means here when x goes to negative infinity, the y value actually reaches 0. It goes towards 0. It doesn't go, it doesn't reach 0, but it goes to 0, right? It goes towards 0, right? Okay. At the same time, okay. So actually the graph will go on like this, right? Okay. When x decreases, the graph will go towards this. Okay, this point. At the same time, here in this region, x is actually decreasing with x. X has to decrease with x. So the graph will be like this. At the same time, look at here, okay, right? When x is smaller than minus 1, the graph is actually concaving down. Concaving down means the graph has to be like this, right? Like this means it can be like this, or it can be like this, or it can be like this. Okay, you can just divide it, right? It can be like this or like this. All of them are actually concaving down, right? It has to be here. At the same time, it has to decrease, and it has to concave down means the graph has to be like this. Okay, right. After this, in the range minus 1 to 1, actually the graph actually increases with x. Graph actually increases with x. Alright? Okay. So here, right, the graph actually increases in this range. Within minus 1 and 1, graph actually increases, and here is the maximum point. Okay. So where does this graph actually intersect the x-axis and y-axis? It's obvious this graph is actually goes through the origin, right? When x is equal to 0, right, according to this equation, what about y? Y is equal to 0. We substitute 0 here, right? In this equation, y is also going to be y is also going to be equal to 0. So the graph actually goes to the origin, right? Okay. So in this region, right, the values actually increases, right? Okay. Fine. After one, actually, fx decreases. Fine. At the same time, look at this graph within minus 1 and 2. Within minus 1 and 2. Within minus 1 and 2, the graph is actually concaving down. Yes, it is concaving down. If you have a part like this in the graph, right? It is concaving down. Right? This is concaving down. Right? If you see something like this, right? It's concaving up. Okay. So in this gap, within minus 1 and 2, the graph is actually concaving down. Yes, it is concaving down. Alright? But when it's greater than 2, actually the concavity is changing here. Right? When x is greater than 2, the graph is actually concaving up. Concaving up means the graph should be like this. Or it has to have a part of this graph. This part of this, okay? Okay, it can be like this. If you divide this one, it can be like this or it can be like this. Okay? Right? When x is greater than 2, right? The graph can be like this or this, but when x is greater than 2, it has to decrease. Right? It is actually increasing, so it can be like this. You cannot take this one. Right? This is decreasing. This is decreasing. So graph goes like this. Alright? So this is the graph, and this is the concave point, right? So sorry, it's the inflection point here. Here the concavity actually changes. This is the maximum point, right? The graph actually goes to the origin, right? So this is the graph of this particular function. Okay. Hope you have understood this. Okay. Please, so just go through the things that I taught you and try to understand this. So hope you have understood this topic, this problem, and please subscribe and like my channel. Thank you very much.